There we go. Okay, so hello everyone and welcome back to the Tutte Colloquium. Today we're very lucky to have Chandra Chekuri from the University of Illinois. Professor Chekuri received a PhD from Stanford in 1998 before working at Lucent Technologies and then moving to UIUC in 2014. Chandra works on a wide variety of topics related to the analysis of algorithms and discrete optimization. Today he's going to tell us about the densest subgraph problem. So please go ahead, Chandra.
Great. Thank you for inviting me. It's a great pleasure and an honor actually to speak in the Tutte Colloquium and in particular at C&O. And hopefully this talk will be of some relevance to some of the topics which have the foundations of which have been laid at Waterloo. So it's really my pleasure. So let me get started. Feel free to interrupt and ask questions. It's actually the talk is really I mean the ideas are simple and mostly connections. So I think that's what I'll try to emphasize. And this is joint work with Kent Conrad, who was a previous student but currently faculty member at Purdue, and current student Manuel Torres. And yeah. So let me start by defining the problem that I'm going to focus on for the most part. And this is what's called the densest subgraph problem, right? And the input is just an undirected graph. I'll assume it's, I'm not going to work in the weighted case for simplicity, just a simple undirected graph. And the goal is to find some notion of a dense subgraph. And there are many notions, but the simplest one is perhaps this one, which is that for a given set of vertices, its density is simply defined as the number of edges inside that set divided by the size of the set. So E of S is a set of edges contained in the set S with both endpoints in S, and you want to find a dense subgraph or a subset, right? So we'll define lambda star to be the optimum value of this quantity over all subsets of the graph. And here is an example. Right, it's a graph, and that clique 4 clique turns out to be a dense subgraph of density 6/4, right? And that's what you want to find. There could be many, but you want to find one of them, right? And in fact, why is it interesting? It's a simple problem that somehow also turns out to be polynomial time solvable. So somehow we like things that are polytime solvable because then somehow we can build on it for various reasons. And it has, I think, a variety of nice connections to algorithms and combinatorial optimization. That's another reason I like it. And I think there are many people study it because it has applications. I'm not going to focus on them in this talk. I can't say that I really know whether they're really applicable, but a lot of papers on this topic. If you look in many of these applied conferences like WebGraph, WWW and KDD, this is one measure of finding some community detection or some subgraph that has some information when you're doing network analysis. There are very many ways of doing it. And this turns out to be one such thing. And the fact that it's polytime solvable makes it a somewhat attractive feature. In fact, there is this whole area called dense subgraph discovery. And part of our motivation came from this many different variations that people seem to study. And let me just tell you a few things. I mean, not really in terms of details, but some examples of what people study in this area, right? So the general goal is to find some notion of density, right? And density is typically defined as a ratio of some function of the set of vertices or some set divided by the size of the set. For example, why only count the number of edges in the graph? Some people count the number of triangles in the set, right? Or some cliques in the set. Right. So instead of counting edges, you count triangles or triangles plus cliques or triangles plus edges, whatever you want to define, some function of the set you are looking for. And you can define it for hypergraphs, and you can define some other measures. For example, recently, Benson, Kleinberg, and Welt defined this p mean density, where instead of counting degrees, you count degrees raised to the power of p. You can do directed graphs, you do constraint versions. So there is some space of problems here, which all try to find some notion of density, right? So I'll abstractly use f of s to denote some function, right? And now let me see why, let's understand what classes of problems in this space are polytime solvable, right? And I think, the densest subgraph was first shown to be polytime solvable by, I think, Picard and Karain, or maybe there are some previous ideas too, but this is the earliest I know of. And then subsequently Goldberg by reduction to flow. So you can reduce solving densest subgraph to flow. And I don't know if it was known before, but there's a folklore reduction to submodular function minimization that we'll see soon. And then, in 2000, Moses Charikar gave a nice LP relaxation, which will be very important for this talk. So I'll mention it when we come to that, right? So there are three different ways. Now let me discuss the connection to submodularity and supermodularity, because that also will be an important connection for the talk. I hope many of us know here what submodular set functions are. Right, a real valued set function on say a ground set V, which is useful because we are thinking about graphs also, is submodular if it satisfies this standard inequality f of a plus f of b is greater than or equal to f of a intersection b plus f of a union b for all sets. And there's also an equivalent definition using marginal values. The marginal value of V to a set A is simply f of a plus v minus f of sorry, this is a typo here. I'm sorry about that. Cut and paste does that, right? So it is the marginal value of V to A is bigger than the marginal value of V to B whenever A is a subset of B. So we think of A and we think of B, and V is outside, and the value of adding V to A should be bigger than the value of adding V to B. This is well known. And what is supermodular? Supermodular functions are negations of submodular functions, or you can define them directly. F is supermodular if f of a plus f of b is less than or equal to f of a intersection b plus f of a union b. I will use some notation. The marginal value, to keep it compact, I will use f of v given s to be f of s plus v minus f of s. And for supermodular functions, this means this is increasing, while for submodular functions, this is decreasing. The f of v given s is a monotone function of s when it is a supermodular and monotone increasing function, and for its submodular, it's monotone decreasing function. Okay, so why are we interested in this, right? Because if you look at a graph and you look at this function f of s is equal to e of s, then that is supermodular. Well, we all know that the cut function is submodular, and this e of s function is because it is, you can express it as a difference of a modular function and a submodular function. It is supermodular, right? Okay, so so instead of thinking about the graph case, we can define the densest supermodular set problem, where the input is a supermodular function. We'll assume it is non-negative and monotone for simplicity. I mean, not for simplicity, for application, that's an interesting case. So we'll restrict our attention to non-negative supermodular functions. And what is the densest supermodular set problem? It is, given the supermodular function has some value oracle, find the set which maximizes f of s divided by s, the size of s. Now, this is a generalization of the densest subgraph problem, right? Because we saw that the function e of s is supermodular. So this problem is solvable in polynomial time, because if you look at the decision version, if you want to know, is there a set such that f of s over s is, the size of s is at least lambda? Well, you just do the transformation, and it is true if and only if lambda times cardinality of s minus f of s is less than or equal to 0. And you can check if there is such a set by appealing to submodular set function minimization, which is polytime solvable. So, I mean, one reason why densest subgraph is solvable in polynomial time is because of this, but this also shows that any dense supermodular set problem is solvable in polynomial time, and this is well known in the literature. Yeah. Okay. So, I mean, why did I get interested in this problem and this topic? There have been a lot of recent papers on this area in this problem, and the reason is that the emphasis shifted from exact algorithms to approximate algorithms because the graphs are very large and the data is very big. So people wanted to solve these large-scale problems efficiently, and while the classical results on polynomial time solvability via flow and submodular function minimization are nice, but their exact algorithms are slow for many of these large data sets. And because also of these large data sets, there have been many papers and ideas on streaming algorithms, parallel algorithms, dynamic algorithms, and also these variations in the objectives that we already discussed, and because the data analysis applications, right? So, there have been a lot of results and interesting results, both from a practical point of view and also from a theoretical point of view, interesting ideas. And very concretely, I was sort of browsing the papers on one day and found this paper which intrigued me. There's a conjecture which I'll come to later on that sort of caught my attention, and I got interested in that, and I'll mention it. And the other connection that also was of interest to me was sort of like this fast approximation algorithms for a certain class of linear programs that come up in this area. And so there is some this mixed motivations got me interested in this problem, and so I'll tell you a little bit about the those things as I go along. But I want to mention the results that we obtain at a high level before I go into some details. Okay, so basically, what we can get, which are new, I guess, is that if you want to solve the densest subgraph problem in a graph with m edges, then you can get a 1 minus epsilon approximation in essentially near linear time for any fixed epsilon. So in particular, the dependence on epsilon is only one epsilon as opposed to epsilon square. So m polylog n or epsilon time, you can get a 1 minus epsilon approximation, right? Which is currently the fastest algorithm for this problem in terms of approximation. And the second thing is that we answered affirmatively this very interesting conjecture made in this paper that will take me some time to get there, but we did answer their conjecture and affirmatively. And the thing that also of interest to me is that we made some connections to show that supermodularity is a useful way to sort of unify some of the results in the literature. And in fact, the way we answered the conjecture came about because we thought about supermodular functions rather than just the graph case. And I will highlight that towards the end of the talk. So the paper is really about some nice set of connections rather than any one result being very difficult. And so hopefully I'll be able to convey the ideas to all of you in a very accessible fashion. So feel free to ask questions if you have. Okay, so now the rest of the talk, I will start with I think the Charikar's LP relaxation, which has been very influential for this paper for sure, but for also in the literature, and it opened up several nice directions. I'll start with that, and I'll tell you briefly about the flow-based approximation algorithm, and talk about this greedy peeling algorithms and some variations of that, and how we resolve this conjecture made by this set of authors. Okay, so that's the plan. Okay. Okay, so Charikar came up with LP relaxation for the densest subgraph problem in 2000, and it's very simple and very nice and elegant, and it showed that in fact this LP is an exact relaxation for the densest subgraph problem. Okay, so how did he do it, right? So okay, I want to maximize this function, right? It's a ratio function, E of S divided by S, right? And so suppose let's think about how we can model it as an integer program, right? If you want to think of it as an integer program, you have this, you want to know which vertex did you include in your set, right? So we'll have an indicator variable ZV to say, do I want to include V in my set S or not? And I also have an indicator variable for each edge of the graph to say whether I include that edge in my set or not, right? So I'm trying to find the subgraph, right? Okay, now the problem is that it's a ratio problem, right? It's a little bit hard to write this because it's a ratio of two quantities we want to capture. So he normalizes it. Instead of saying that I want to choose a set of some size, he says, okay, I'm going to make it fractional, and says sum of the ZV equals to 1. Okay, that is saying that I want to pick some set, right? Now, when can I pick an edge UV in my graph? I can pick an edge UV in my graph only if both U and V are included, right, in the integer sense. So the way to model it is I say, okay, I cannot include an edge unless both U and V are 1. So I'll write this constraint XUV is less than equal to min of ZU ZV. Okay, and then I maximize the number of edges I pick because I'm going to normalize the set size to be 1 fractional. Okay, so I hope you see the relaxation, right? That this is an LP relaxation for the densest subgraph problem. Yeah, very simple relaxation, right? Any questions on that? Okay, the interesting thing, is that Moses showed that this LP is optimal in the sense that it's exact relaxation for the densest subgraph. The optimal value of this is precisely lambda star. So there's no integrality gap. Okay, which is nice, right? And it's a very simple looking LP. Okay, but let's look at the dual. The dual turns out to be quite useful, and we'll see that. What is the dual, right? Dual has a nice interpretation and has a nice applications. And so let's see what the dual is going to tell us, right? The dual is like some kind of a assignment problem, like a fractional matching problem, right? So it has a objective D, right? D, think of as some fixed constant for now. It's a variable. It's sort of, in fact, maybe it's easier for me to, I'll explain the dual in a little bit. Maybe it's easier once I tell you the picture of how to think of the dual as a flow problem, but I'll come back to that. Let's see. What is interesting about the dual, right, as opposed to the primal. If you look at the dual, don't worry about the interpretation. If you fix a value D, then it's what is called a mixed packing and covering LP of, right? What it means is that the LP has only positive entries everywhere. Okay, there are no negative entries in the LP. Okay, and so it has some nice features, and because of that, we know good ways of solving this LP approximately and quickly using some standard techniques like multiplicative weight updates. So that's a nice advantage of the LP that Moses gave. First, it's an exact relaxation, and the dual has some nice features which allow us to solve it efficiently and approximately. Even though it's an LP, it has some structure which allows us to solve it fast. And so in particular, you can, using standard techniques with some variations, you can obtain a 1 minus epsilon approximation just by solving the LP using standard solvers in the sense in the literature, right? Using multiplicative weight updates. And then, people want to improve this because, epsilon square dependence may not be so good. And so there's a big open question in this area. Is there an algorithm which reduces the dependence on epsilon for a 1 minus epsilon approximation to 1 epsilon, right? And that's open. And then some special cases are known, and it's very nice connections to optimization. So that we don't know yet. But people wanted to get this result of some weaker form. And so Boob, Salani, and Wang showed that you can get a dependence of 1 epsilon, but you pay something extra over this where the factor is the maximum degree of the graph. So if the degree is small, it is good, but in the worst case, it's not so good. If the degree is n, you're getting maybe not such a good algorithm, right? But anyway, the point is that the LP allowed people to use some nice techniques in the literature to get fast approximation algorithms, which weren't so easy to see before the LP was there. And then that's the main point of one of the main points of this LP relaxation. Okay, there are many other advantages too. Okay, so now what we will do is that we will actually get 1 epsilon dependence by using not an LP solver, by using something using a network flow, right? So now let me interpret the dual as a flow problem. It's a quite nice flow problem, right? So what is the dual saying, right? The dual is saying, okay, think of the original graph G, create this new bipartite graph, okay? On one side, you put the edges of the original graph. On the other side, you put the vertices of the original graph. And it's saying, okay, you have to assign every edge of the original graph to one of its two endpoints. Okay, so it's an assignment problem. The dual is saying, assign the edges of the original graph to the vertices of the original graph, and an edge can be assigned to only one of its two endpoints. Okay, and do it in such a way that you minimize the maximum load on any vertex on the right side. Okay, and that's what the dual is telling us. Okay, so, and it's saying, okay, the smallest load that you can achieve by this is the optimum value of the dual. Okay, if you look at the dual, right, you see, it is saying, you have to assign each edge UV of the original graph to U or V, and you want to minimize this maximum load lambda on any vertex. So, and the smallest lambda that you can achieve is the optimum value of the dual, and which by duality is the same as the Moses' theorem that it is the optimum value of the densest subgraph, right? Okay, once you have this thing, you can solve this via flow, right? It's just an assignment problem, so you can solve it by flow. Okay, and you say, okay, people already knew how to solve densest subgraph via flow, right? Picard and Karen and Goldberg. But surprisingly, this reduction, which is in some sense more natural and simpler, is not the same as the reduction to flow from the past. This is somehow a simpler reduction to flow, which came out of the LP. Okay, so it's very simple looking LP. And so, okay, now we can solve it by a flow, right? That's not surprising. You can use exact algorithms for flow to get coupled with a binary search. Remember that, in the dual, there's a D. So you have to do binary search for lambda to find the best, lowest value of lambda such that it is feasible. Okay, so nothing new there if you want exact algorithms. So what we do prove in this paper is, I think, a nice result. Which says something interesting, right? It says the following, that, you can approximately solve this flow network and it'll give you a good solution for the LP. Okay. So what does it mean to approximately solve the flow problem on this network? Approximately solving flow in this network, we characterize it by saying that if you try to solve this problem using augmenting path algorithm, say for instance, which is a standard flow algorithm, you can stop the augmenting path algorithm when the shortest augmenting path length is roughly log n over epsilon. Okay, so our result is that in some sense, you don't have to go all the way and solve the flow problem exactly once you have this reduction. It is sufficient to stop the flow algorithm when the augmenting path length is roughly log n over epsilon. Okay. And so you can use standard technology, and this is a structural result. And once you have this result, you get this corollary that you can compute a 1 minus epsilon approximation for the densest subgraph problem in m polylog n over epsilon time. Okay, so remember that that's what we wanted to achieve using LP techniques, right? In a very general sense, but we don't know how to do that yet, right? The open problem is, for any mixed packing and covering LP, can you get an algorithm which has only one epsilon dependence for an approximation, right? That's a very nice open problem in positive LPs. We don't know how to do it in general, but for densest subgraph, we do get that result using flow. Okay, so it's a nice observation about this short augmenting paths being sufficient to get a good solution for in this flow network. Okay, so I think people know about matchings, right? If you have short augmenting paths, if you don't have short augmenting paths, you're always close to optimal. This is some analog of that in the density sense, that but the augmenting path length has to be about log n over epsilon, not 1 over epsilon. It is sufficient to make it sufficiently long that then you'll get a good approximation to what you want. Okay, So that's one result. I'm not going to go into the details because it takes some time, but it's a structural result about short augmenting paths giving good approximation. Any question on that? So the LP led to a flow network characterization, and from the flow network characterization, we are able to show that short augmenting paths are sufficient to get you a good approximation to the problem. And that gives a very fast algorithm. It's not yet implemented, and we don't know how well it will work in practice. But it's a fastest asymptotically known algorithm for an epsilon approximation. Yeah. Questions? Okay. All right. So then, I mean, that's one result, and now I'll go to a second aspect of the talk about greedy algorithms that have been very popular in this space, and the conjecture that refined that. Okay. So in fact, one of the reasons Moses's paper was quite influential was not because of the LP, which also is influential, but also because he proved via the LP that a very simple greedy algorithm for densest subgraphs gives you a half approximation. And people love that algorithm because it's so simple and it's so efficient that they can run it on many big graphs, right? Well, a flow is harder, right? So what is that simple greedy algorithm? Here is a simple greedy algorithm for densest subgraph, right? And it was actually defined by Asahiro et al., but Moses analyzed it to show that it actually gives a half approximation. And because it has nice approximation, people liked it, and it's very fast. So, so what is it? Very simple. You start with the graph, and you take out the minimum degree vertex, okay, and put it aside. And then in the remaining graph, take out the minimum degree vertex and put it aside. So you're peeling away the minimum degree vertex at each step, okay. So what happens, at the end, you get an ordering of the vertices, v1, v2, vn, right? And it's a very simple algorithm, right? You start with the graph, remove the minimum degree vertex, and keep doing it, and you get an ordering. And then once you get the ordering, you look at all possible suffixes of this ordering and take the best suffix in terms of the density. Is the algorithm clear? So here is maybe an example, right, to show also that, and so what did he prove? He proved that, the Chekuri proved that, this is a half approximation for densest subgraph. Because it's such a simple algorithm, it's very fast. Yeah. Okay. So, and here is a nice example showing why the half is tight. It's you can't get better than half with this algorithm. And because I will use this example again, let's see this, right? Just also to see whether we understand the algorithm. Okay, here is a graph. The graph consists of a bunch of cliques, but for this example, there are cliques of size 4. And it also consists of a bipartite graph, which consists of 3 vertices on the left and a lot of vertices on the right. Okay. So what is the densest subgraph in this example? Okay, you can look and see that, that this is the densest subgraph, right? Why? Because if you look at the density, the average degree of everybody is roughly d, right? I mean, the number of edges is in this bipartite graph. It is d times d, and how many vertices are there? It's d, so it's roughly d, right? While if you look at the clique, its density is only roughly d over 2, because there are d times d minus 1 over 2 divided by d, right, in a clique of size d, right? So this is the densest subgraph, okay? But what does the peeling algorithm do? If you kind of stare at it for a little bit, the peeling algorithm, you break the ties. You can avoid breaking the ties by doing a slight perturbation, but let's not worry about that. You can check that, if you balance things out, you will peel all the red vertices first because they have degree 3, and the clique vertices also have degree 3. And if I'm being adversarial, I can force you to peel the red vertices first. Okay, so the ordering you get will have all the red vertices before all the clique vertices. Okay, and now remember the algorithm takes only the suffixes, right? So essentially the algorithm is forcing you to take all the cliques, but the average density of the cliques is only d over 2, while you should only take this bipartite subgraph, right, which has density d. So the peeling is not giving you the tight answer, but it is giving you, the proof says that you'll get half approximation and half is tight, as this example shows. Yeah. Okay, so that's nice, and because it's a simple algorithm, people use it in practice a lot, right, in some variations. And then people started saying, okay, this peeling idea is very nice. There are other reasons why people care about peeling. They have some connection to k-cores and things in graphs. So for every other objective, people started using peeling, right? And so there are now a number of papers, and sometimes they get confused about what is the right order to peel, because they say, oh, and then we got interested in saying, is this really an interesting algorithm only for graphs, or is it because it's something to do with supermodularity, right? So now let's consider the more general problem of supermodular density problem. And you say, is there a peeling algorithm for supermodular density, and is there a useful, is it can you prove something about it? Is it a graph result or is it a supermodular function result, right? So there's a very simple generalization of the peeling algorithm to supermodular functions. What would you do, right? You'd say, okay, what is the first thing you would peel away? Why did we remove the lowest degree vertex in a graph? Because we think it's not interesting, right? It's not part of the dense subgraph, right? So same reason, if I give you an arbitrary supermodular function, what is the first element you need to remove? We no longer have a graph. You remove the element which has the smallest marginal value with respect to the remaining set. So the first element you'll take away is the vertex of the element which minimizes the marginal value of that to v minus v. That is the right generalization of picking the smallest degree vertex. Okay, and then you keep doing it recursively, right? You again compute an ordering v1, v2, vn, and again take the best suffix. Okay, and now we can ask, is this a good algorithm? Can you characterize its performance? Right? What can you prove for this graph, right? For this more general setting. Okay, and so what we did was we said, how do we analyze this? And we defined this parameter called CF for any function, supermodular function CF. What is this parameter? This parameter says compare the value of f of s to how big is the sum of the marginal values of the elements in the set compared to the function value on the set. This is a feature of the function, right? It is a function for any given supermodular function. You can define this bound called CF, right? And by supermodularity, this marginal value sum is greater than or equal to the f of s. So this number is some number bigger than or equal to 1. Okay, and so it's just some parameter that you can define with respect to the supermodular function. And we're using a very simple proof. We showed that for any supermodular function, the peeling algorithm gives you a 1 over c of approximation. Okay, and let's see why it's useful, right? Let's look at the case when we have a graph. What is this parameter CF when it's a graph? Well, it is simply, if you look at a set of vertices, this marginal value is simply the degree of the vertex v in the graph. Okay, so what are we measuring? We are measuring the sum of the degrees divided by the number of edges in the subgraph. But that's exactly 2, right, for any subset of vertices, right? So this parameter CF, when you specialize it to graphs, is exactly 2. So what we are proving is a generalization of the peeling algorithms analysis, right? We're saying you're getting half approximation for graphs, but it's really not about graphs. For any supermodular function, you'll get 1 over c of approximation if you do this peeling. Okay. And why is it nice? Because first it shows that it's really that you can characterize the performance of the greedy algorithm for any supermodular function, and several results in the literature can be just seen as corollaries of this. That this is a simple proof and simple analysis. Okay, because it's so simple, let me do the proof for you. Right, I'm not going to do one proof in this talk, and this is a very simple proof. So let me do it quickly for you. Yeah. Okay. Okay, and the proof goes back to a simple argument that Kuller and Saha gave. Charikar proved greedy analysis with respect to the LP, and then Kuller and Saha gave a very simple combinatorial analysis, and we're just going to generalize it. So it's nothing very difficult in this. It's just that we introduce this parameter because that's what seemed to be the right thing to do to analyze, right? And then it turned out to unify all the existing peeling analysis, right? Okay, so how do we prove this, right? Okay. Let S star be the best density subset. Okay, we don't know what it is, but it is something. Okay, a very simple observation is that if S star is the optimum set, then for every vertex in that set, the marginal value with respect to S star minus V must be at least lambda star. And it's nothing about supermodularity, right? If S star is the optimum, you should not be able to take any V outside V from S star and still be good, right? So the marginal value of every vertex in S star should be at least lambda star. Otherwise, S star minus V would be a better set than S star. This is nothing to do with supermodularity, just with monotonicity. This is a simple observation for any function as long as it's monotone. Okay, I haven't used supermodularity yet. Okay, now let's understand what the greedy algorithm is doing. It is kind of taking vertex and taking them out, taking them out, taking them out, right? Let Vj be the first vertex we take out of S star in the algorithm. Okay, remember S star is sitting somewhere, and Vj is the first vertex we touched from that S star. And I'm going to prove that Sj is itself very good. And remember, we are going to try all suffixes, right? And since Vj is the first vertex in the peeling order, we are going to try Vj to Vn as one of the suffixes, and I'm going to prove the density of this Sj is good, right? And how am I going to prove that? Well, let's look at any vertex which is peeled after Vj, including Vj, right? Okay, because the peeling algorithm is picking the vertex with the smallest marginal value, at that moment, the marginal value of every element Vi for I greater than equal to j must be at least as good as the marginal value of Vj. Okay, so this is from the algorithm. And now this is from supermodularity. I claim that the marginal value of Vj to Sj is at least Vj to S star, because S star was not touched so far, right? Remember, Vj was the first vertex in S star. So that means that S star is sitting here, and this is Sj, and Vj is here, right? The marginal value of Vj to S star can only be smaller than the marginal value of Vj to Sj, because S star is still inside Sj because of supermodularity. So this is supermodularity, and this is simply from the fact that Vj was the smallest marginal value I peeled because of the algorithm. And this is from the previous observation that the marginal value of Vj to S star should be at least lambda star. That's just because that's the optimum set. Okay, now we know you just do the calculations, and you say, okay, what is the density of the set Fsj by Sj? Well, I just write Fsj by Sj, and I multiply and divide by this quantity. What is this quantity? The sum over all elements in Sj, the marginal value of Vj to V to Sj. The sum over all marginal values of vertices in Sj, and that I'm dividing and subtracting. And by our claim, this is bigger than lambda star, and this is our definition of CF. And because that is minimized, I mean, it cannot be less than 1 over CF, because that's the definition of CF. Okay, and so you get that that it is lambda star times 1 over CF. Okay, so it's like just, I mean, it's a very simple proof using supermodularity. The main observation is that this quantity CF somehow characterizes the performance of the greedy algorithm for all supermodular set functions. And it's very simple quantity. I mean, we haven't seen this measure of supermodular functions being used before. I am sure it is, I mean, it may have been discussed before, but we found it interesting that this shows up as the performance of the greedy algorithm, right? So if you have any supermodular function, you can analyze what this value is, and you'll get a bound on the approximation. Okay, so that's about the greedy algorithm, right? And so it unifies previous results. So now let me talk about iterative peeling and the conjecture that made us go down this path, right? And this is a conjecture of Boob et al. Boob, I mean, I forget the authors' names. There are several of them, right? 7 authors. So what did they do, right? You know, they looked at this peeling algorithm, and we see that it gives a half approximation for graphs. Okay, half is good, not so bad. But when you try to, they wanted a better algorithm, right? They say, okay, half is good, but you know, it would be nice if we could come up with an algorithm which had some improved approximation, but we want it to be simple and efficient. So they are trying to go from half to 1 minus epsilon, right? And do it in a way so that the algorithm is still efficient and simple. And they came up with this heuristic. And the heuristic has some motivation, but they couldn't analyze it so carefully. So they call it greedy plus plus, right? And giving good names, I guess, is one of the things you have to do when you do algorithms, right? Or at least they have more catchy names, flowless, something. But so I call it iterative peeling, right? Okay. So it's a variation on the greedy algorithm, right? You know, and so what is the variation, right? And so it's sort of like you do the peeling many times, right? Iteratively, and you take the best among all the iterations you run the algorithm. Okay, so in each iteration you are changing how you peel the vertices, right? Okay, and so how do you do that? You maintain something called load, and it's well motivated, but it will become clearer later. So initially the load of every vertex is 0. And then what do? You just run the greedy algorithm, right? Your first iteration of your algorithm is basically the same as the standard greedy algorithm. Now, in the second iteration, you start behaving differently. And how do you do that? Well, after the first iteration, you look at when you peel the vertex, you assign all the edges that were incident to that vertex to this vertex. So the load of the vertex is the degree of the vertex when you peeled it. Okay. So in the second iteration, you don't peel based on the degree, but you peel based on the degree plus the existing load. Okay. So in each iteration, when you peel the vertex, you assign all the current edges that are incident to that vertex and add it to the load. And in the next iteration, it will influence the peeling order. Okay. So, and then you do it many times, and you take the best suffix you get among all these orders, and that's the algorithm. Okay, so let me run this algorithm for a couple of iterations on this example, so that you see what's happened. Okay, so remember this graph, right? You know, what was the first iteration? In the first iteration, you pick the vertex with the smallest degree and take it out. And I'm being adversarial, or just to break ties, I'm picking the red vertices one by one, right? Because when you take the red vertex, it has degree 3, right? Every vertex has degree, I mean, all the click vertices have degree 3, all the red vertices have degree 3, the yellow vertices have high degree, right? Because there are a lot of red vertices. So among the vertices of degree 3, I chose to pick the red vertex, right? And then I take out one red vertex, I put it, then what do? I take the next lowest degree vertex, the red vertex still has degree 3, another red vertex has degree 3, so I take it out. And so keep peeling the red vertices. And then, you know, when I get to only 3 red vertices, then some noise creeps in. There's a 3 yellow and red, they form a bipartite clique of size 3 by 3, and then things start misbehaving a little bit. So it's not so important, right? And that's why you get this slight mix between red and yellow there. So it's not very important. And then you start peeling the clique vertices one by one. Okay, that's the first iteration, right? We already know that the algorithm's performance is half, and that's tight on this example. But what about the new algorithm? What did the new algorithm do? In the first iteration, it behaves exactly like the standard greedy algorithm because the loads were 0. But when we did the first iteration, we keep track of the load induced on the vertices during the peeling. So what is the load of the red vertex when I peeled it? I assign all these edges to this. So the load of this vertex is 3 when I peeled it. So all these vertices get load 3, and then this guy gets to 2, 1, 1, 0, right? That is the load we induced in the first peeling. And then you get 3, 2, 1, 0, 3, 2, 1, 0 for each of the cliques as you peel. Yeah. But what about in the second iteration? In the second iteration, the algorithm is to peel according to the load plus degree. So what is the vertex with the smallest load plus degree when you start the second iteration? Well, the red vertices now have load 3 and degree 3. So their load plus degree is 6, right? Okay. But what about this vertex, right? You know, this clique vertex had a load 0 and it has degree 3, right? So they become more attractive for peeling in the second iteration. Okay. So now you start peeling the clique vertices first. So is the algorithm clear what the algorithm is doing in the second iteration? Yeah. And now you can see that it is doing the right thing. I mean, you know, in this example, at least it's doing the right thing because it has put all the clique vertices first. And so the optimal suffix is sitting in the right side. So in the second iteration, it will actually find the optimal solution if you, right? So somehow it is found the optimal solution in 2 iterations. Okay. Anyway, that's their algorithm, right? I didn't come up with the algorithm. They came up with the algorithm. Okay. And this is what attracted me to this, right? They say, oh, it seems right. Okay. And they conjectured the following very nice thing, that it will converge to a 1 minus epsilon approximation in only O of 1 over epsilon square iterations. Okay. And they implemented it. It works amazingly well and very fast in practice. Okay. And they have data. We also ran it. It's extremely fast. You know, it's very nice, right? It runs very fast on at least practical large graphs. You can run it on, I don't know, millions of nodes, and it's because so simple, it converges extremely fast. And they made this very bold conjecture. Okay. Right. And they didn't prove anything better than half. They didn't know how to prove that even converges to optimum solution. Okay. So any questions on the algorithm or the conjecture? Right.
Yeah, you mentioned a while ago that it was well motivated.
Sorry, can you repeat it?
You mentioned that the idea was well motivated.
Yeah, I'll motivate it. Yeah, I mean it is well motivated because of the. I mean, so it's motivated by the dual LP. Okay. And but not in an obvious way. Okay.
Okay.
Yeah.
Are you going to describe that, or you just?
Yeah, I'm going to describe it.
Okay.
Yeah.
Thanks.
The rest of the talk is about. All right. Okay. Okay. So. So. I mean, the algorithm is well motivated because it seems like it's a sort of like there's some connection to the multiplicative weight update algorithm to solve the dual, and these loads are the dual variables basically. Okay, and that in a certain sense they are, right. The only thing is they couldn't prove why this works basically, right. Even though they thought it is coming from the multiplicative weight updates, they couldn't prove that this works. Okay. And so because it's hard to relate what the algorithm is doing directly to the multiplicative weight updates, right? And so that was somehow the reason why it was difficult. Okay. Okay. So we proved that this converges, right? But not in the strong form they said. Let me state the theorem, and I'll come back to how we proved it, right? So we proved that it will converge to 1 minus epsilon approximation, not in 1 over epsilon square iterations that they claim, but in a slightly weaker bound, which is slightly or much worse bound, depending on how you see it. The dependence on epsilon is 1 over epsilon square. That's okay. But we have this term, right? Log n times the degree divided by lambda star. Okay, so at least we are proving it is convergent, right? Okay, so it converges to 1 minus epsilon approximation in this many iterations. Okay, in fact, what we did was we proved it not for the graph case, but we proved that for any supermodular function, the variation of this Peeling algorithm will converge. Okay, so it's not really only about graphs, but for any supermodular function, you can generalize this Peeling algorithm in the most natural way, and it converges. Okay. Okay. So
Chandra, just to let you know, it's been 50 minutes. So if you could wrap up in like 5 minutes, that would leave time for some questions.
Okay. So yeah, I guess I had a lot of things there. So what was the key insight that allowed us to prove this, right? And supermodularity was really the key. And this was our first observation. If you look at Charikar's LP, okay, where did it come from, right? And I'm going to rewrite the LP where I replace the variables by instead of having this variable that xuv is less than equal to zuzv, I'm just going to put it in the objective. Min zuzv is my objective. Okay, and you just have this constraint, and you have this, and you can see that it's a concave program. And that's the reason why it's a linear program if you write it this way, but it's really, if you put it in the objective with only the variable zv, then it's a concave program. Okay, you say, okay, what is this concave program? Where did it come from, right? It turns out it is nothing but the lowest extension of the function e of s. Okay, so in fact, what Moses's LP is doing is actually generalizes to the densest supermodular set function problem. Okay, so suppose I didn't know anything about Moses LP, right? And I say, okay, look, I want to solve the densest supermodular set problem. And I say, okay, write a mathematical programming relaxation. Okay, now there are no edges, no graph, nothing, right? How can I write a mathematical programming relaxation? Well, I say, okay, how do I extend supermodular functions to the continuous domain? Okay, I know one trick, and that is to use the Lovaas extension. Okay, because it's a concave or convex program depending on it's supermodular or submodular. So I can write this convex program via the Lovaas extension of a supermodular function. Okay, and in fact, Moses's LP is a special case of this, and it's very easy to prove that this LP is exact for densest supermodular set problem also, just using properties of the Lovaas extension. Okay, so you can prove that there is a nice LP or nice concave program sitting underneath the densest supermodular set problem. Okay, so but that's not enough, right? Okay, well, what do you do with it? So our second insight is that you have to use Edmonds, okay, not just Lovaas, right? Okay, what do I mean by that, right? So we didn't know how to prove that this thing converges, right? We had this intuition, and as Jim was asking, and I'll after the talk, if people have time, I'll explain it in more detail. We were able to rewrite this this concave program via some simple transformations into a linear program using an exponential number of variables by a characterization of the Lovaas extension in a different way, right? And that is to say that you can rewrite the Lovaas extension, which was natural for us in the first step, as a minimization over all possible permutations of the ground set of this function q sigma times x transpose. Okay, so we can rewrite the concave program as a large linear program. Okay, and I don't have time to explain that, but when you rewrite this concave program into a large exponential size linear program, it becomes much more clear why you get this orderings on this greedy algorithm. Okay, so this, with respect to this new linear program, we are able to show that the iterative greedy algorithm is essentially a multiplicative weight update algorithm with respect to this large implicit linear program. Okay, so there are some technicalities because it's not quite the same as multiplicative weight updates, but some tweak of it. Okay, I won't go into the details, but the main technical insight is that once you go into the supermodular world, orderings of vertices becomes a natural object of study. Okay, it's not surprising that the greedy algorithm is working with orderings, because orderings are natural when you work with supermodular functions or submodular functions. Okay, so the message I want to convey is that by reformulating the linear program as via the Loas extension and then reformulating that Loas extension based concave program via this other way of looking at the Edmonds extension, I'll call it, it becomes transparent what the greedy algorithm is doing in an iterative sense, and we are able to make a connection to multiplicative weight updates, okay, which is an iterative algorithm, and putting all those things together, we get our result. Okay, so really it is seeing the problem in the right way, first using supermodularity to sort of see that the LP of Moses is not really for graphs, but it's really about supermodular functions, and then reformulating that concave program in a linear program, and then observing that the iterative peeling algorithm is really a multiplicative weight update algorithm with respect to that linear program. Okay, that gives us the convergence guarantee. Okay, so and as a corollary, we are able to show that it works not just for graphs but also for any supermodular function. Okay, so that's really what I want to say, right? So it's really, I mean, there's a lot here. Sorry, I thought I could, right? So in a sense, lifting to supermodularity was key insight to really understand the conjecture. The conjecture was the motivation for the peeling algorithm came from the LP, but it's not easy to see in the LP why the orderings are coming. While if you live in the supermodular world, the orderings become natural. And it didn't come about so easily for us also. It took some time to think about it and rewrite the LP and so on, right? But anyway, that's the main message, that this algorithm is very simple. It works very well in practice, and now we can prove it converges. And it originated from the LP, and we lifted it to supermodularity and are able to get a more general result. So it's a simple algorithm with a good convergence guarantee. So that's all I want to say. Okay.
Okay, great. Let's unmute and thank Chandra for his great talk.
Thank you. I'm sorry, I may have tried to do too much. Right? If you have any questions, I'm happy to answer.
Yeah. So, are there any questions? Yeah, go ahead.
So, Chandra, you say that you don't believe the conjecture of those authors?
In the sense that, okay, I mean, when they made that conjecture, I was initially drawn to that very tight bound of 1 over epsilon square, right? When I say I don't believe the conjecture, what I mean is that is there no dependence on any other parameters of the graph? So we don't have good lower bounds on these algorithms performance. And in fact, and the student is working on trying to understand what are the bad examples for this algorithm. Actually, we don't have actually easy bad examples. We tried, but we couldn't prove that whether this algorithm really takes 1 over epsilon iterations. Is it is there any other dependence. And initially I thought, oh, their conjecture is close to the truth. But now I kind of feel that it should have some dependence on delta or log n or something. It can't be completely 1 over epsilon square, right? So I believe there are other parameters that will influence the running time of the algorithm, right? We are proving, of course, a weaker result, right? So yeah, that's what I meant. So it means that 1 over epsilon squared times something, okay?
Okay.
Other questions?
I guess Jim asked a question. I don't know if he's still here.
Yep, I'm here.
Yeah. So I mean, I underestimated the time I thought I'll take. There is a reason why they came up with this algorithm, and that is if you look at the dual, right, of the LP. Where is the dual? Yeah. Yeah. So if you look at the dual, right, you know, they are assigning edges to remember the flow network. They are assigning edges to vertices, right, to minimize the maximum load. So each iteration gives a load, and so they are thinking of an iterative algorithm which tries to minimize the maximum load by looking at the next iteration to give preference to the vertices which have higher load in some sense, right? So you want to, so it's a very natural, in some sense, measure that to kind of keep track of if you're thinking of an iterative algorithm. So it is well motivated in a sense. The load peeling according to the load that is accumulating is well motivated if you're thinking about multiplicative weight update algorithm to solve the LP. Okay. The main thing is how do you prove that it is correct, right? So the correspondence between this LP and the ordering is not obvious, and that became clear only when we lifted it to the supermodular setting. Okay, maybe there's one way of analyzing it just by looking at the graph, but we found it much more easy to see it once you saw the ordering LP, right? And that is not obvious in the graph case.
Yeah, I certainly don't see. It seems like the second iteration seems sort of natural, but after that it seems weird to me.
Yes, after that it seems weird, right? You know, and in fact, if you start with the ordering LP and just do multiplicative weight updates, you won't get the first iteration as that of the greedy algorithm. So in some sense, I don't believe we fully understand what's going on, in the sense that the greedy algorithm is somehow doing well, right? The first iteration is doing well, and the load-based algorithm is making it go closer to the multiplicative weight algorithm. So because the degree doesn't change, but the loads keep increasing, and in the end, the degrees disappear because it becomes just loads. And then you're closer to multiplicative weight updates. So this is one of the few instances I know where there's a simple starting algorithm which is good, but then it is going closer and closer to the iterative multiplicative weight update algorithm. So it's not a pure multiplicative weight update algorithm, which will be very slow to converge because the first iteration is completely useless, right? It doesn't tell us anything. But the first iteration here is based on degrees, which is giving a good approximation. And then slowly it is going towards convergence. So, I mean, it's a nice phenomenon that you start with somehow a nice heuristic, which gives you a good approximation in the very first round. And then somehow you improve it over time and by getting it closer to a more methodical framework. I don't know too many such examples, and somehow I found it intriguing to think about this. And I'm glad that we managed to solve it, but it wasn't obvious when we started.
Okay, great. So in the interest of time, I think let's just thank the speaker again.
Thank you again.
So for those who want to stick around, we